a normal everyday object into a sealed box, let's say a marble, basic common sense tells you that the marble is sitting in one specific location inside that dark space. Right.
Right, yeah, it has physical coordinates.
Exactly. But quantum mechanics tells us that if you place a subatomic particle into a highly controlled box, it isn't sitting in one spot.
No, not at all.
Until you open the lid and actually measure it, that particle is essentially everywhere inside the box at once. It just exists purely as this smeared out wave of mathematical probability. And welcome to today's deep dive.
Glad to be here.
Today, we are unpacking a genuinely provocative text from Time Traveler's Paradox, which it sets out to dissect the intersection of quantum mechanics, human biology, and basically the whole philosophy of science.
Yeah, it's a huge topic.
It really is. And for those of you who regularly track theoretical physics or follow the debates in quantum field theory, you know the underlying tension here. The math works, right? The
Yeah.
predictions are absolutely flawless.
Flawless, yeah. They've been proven time and again.
But the reality it describes is just deeply, profoundly counterintuitive. It's confusing. And if you're feeling that hesitation, you're not alone. Quantum physics has this reputation for being just impossibly difficult to grasp.
Which is fair, honestly. It is difficult.
Right. But our mission today isn't to rehash the basic equations or prove that it's impossible. Okay, let's unpack this. We want to look at why our brains aggressively reject this reality. By the end of this, I promise, you are going to look at your own hands completely differently.
That's really the goal today. We want to strip away this myth that quantum physics is some kind of, magic and just reveal the tested, rigorous reality underneath.
Yeah, because we have this tendency to treat our inability to visualize the quantum world as a failure of the science itself. Like, we ask, why can't physicists just explain this in a way that makes sense to us?
Well, the authors of Time Traveler's Paradox actually flip that entirely. They argue that the hesitation, that cognitive dissonance we feel, is actually a purely biological problem.
Wait, biological? Like, it's our brains that are the issue.
Exactly. We are operating with this localized macro-scale neural architecture, and it's desperately attempting to decode a non-local microscale universe.
Oh, wow. So the source material actually dives into evolutionary neuroscience here, framing the human brain as basically a prediction engine optimized for the savanna, right?
Right, think about what we evolved to do. We evolved to track predators, calculate the trajectory of a thrown spear, or, gauge the speed of a river.
Things we can see and touch.
Yes. We needed to understand the mechanics of medium-sized objects moving at medium speeds. Our neural circuitry was shaped by things like gravity, friction, and visible matter, not atoms, and definitely not galaxies.
So basically, our baseline intuition is hopelessly biased from the start.
Hopelessly. And that brings up the guiding principle from the text for engaging with modern physics, which is, you should never assume reality must match human expectations.
Right.
The quantum realm operates under a completely different set of rules. Probabilities, superpositions, non-locality. These are concepts our physical neurons were literally never selected by evolution to process.
So to the universe, a superposition is just perfectly natural. But to a brain built to outrun a lion, it just registers as impossible nonsense.
Exactly. The science is just the tool that extends our senses into these territories we weren't prepared for.
But I mean, I have to push back on the source text here on behalf of all of us listening. Shouldn't our gut instincts count for something? Like, it leans so heavily into this idea that we're constrained by these savanna engines.
It does, yeah.
But if we are fundamentally unequipped to grasp the stuff biologically, how did human brains even invent the mathematics to understand quantum mechanics in the first place? I mean, we built the Schrödinger equation.
We did.
Doesn't the existence of that math prove that our brains can actually transcend that biological programming? It's kind of like trying to run a next-generation virtual reality game on a dusty 1990s desktop computer. The hardware just wasn't built for it, but somehow we're still running the code.
What's fascinating here is that the text actually resolves that exact tension. It makes a really sharp distinction between biological intuition and intellectual abstraction.
Okay, so how do they separate those?
Well, the math is the bridge. You're completely right that human intelligence is adaptable. What we adapt is our tool set, not our gut instinct. We still can't naturally visualize a 10-dimensional space.
Definitely not. I can barely visualize 3 sometimes.
Right. But we can manipulate the algebraic topology that describes it. Science, and mathematics specifically, becomes this sensory extension of our biology. It's exactly like your analogy. It's the software upgrade that lets our Savanna-optimized hardware navigate the dark.
Okay,
Accepting the limits of our own biological intuition is really the first necessary step to understanding the universe. When biological intuition fails, and it fundamentally fails at the quantum level, the scientific method is the only reliable sensor we have left.
Which perfectly brings us to how we experience that territory on a daily basis. Because, we all learned in high school chemistry that atoms are something like 99.999% empty space, right?
Basically, yeah, a vast emptiness.
We know the nucleus is just this tiny speck compared to the massive electron clouds orbiting it. So if we zoom in, past our skin, past the cells and the molecules, down to the atoms, we don't find solid stuff.
No, you find almost nothing at all.
Which means trees, mountains, planets, and, you and me, we are almost entirely empty space. But the source text pushes past that standard trivia to ask a much more aggressive question. Here's where it gets really interesting. If we are just this buzzing void hovering on a bed of forces, what is actually constructing our physical reality?
Well, we have to unpack what empty space actually means in a modern context. Because it isn't just a vacuum.
Right.
The text really challenges that century-old expectation that at the bottom of reality, you eventually hit tiny microscopic billiard balls.
Like little solid marbles.
Exactly. The assumption that solid objects must be made of smaller solid objects is just another artifact of our macro-scale brain.
Instead, the deeper you go, you find that solidity is an emergent property.
An emergent property, so it's not a fundamental truth of matter. No, it's an illusion. It's generated by forces interacting within that vast emptiness.
I think this is where the text gets just incredibly visceral, because if the chair I'm sitting in right now is overwhelmingly empty space and my body is overwhelmingly empty space, why don't I just fall straight through the floor?
That's a great question.
And more practically, if there are no solid marbles colliding down there, why does stubbing your toe hurt so much? I mean, that feels pretty real to me.
It feels very real. But the mechanism at play there is electromagnetism and the rules governing quantum states. Specifically, something called the Pauli exclusion principle.
Okay, break that down for us.
So when you step on the floor or you stub your toe, the atoms in your foot are not physically colliding with the atoms in the furniture. They never actually touch.
Wait, really? Never?
Never. What is actually happening is a clash of electromagnetic fields. The electrons that form the outer shell of the atoms in your skin are being forced into very close proximity with the electrons forming the outer shell of the wood or the metal.
And because electrons have a negative charge, they fiercely repel each other, right? Like magnets?
They repel each other electromagnetically, yes, but they also obey quantum rules. The Pauli exclusion principle states that no two identical fermions, which is the class of particles that includes electrons, can occupy the same quantum state simultaneously.
Oh, I see.
So as those electron clouds press together, they require vastly more energy to overlap. That massive, invisible, energetic pushback is what gets transferred up through your nervous system.
And then my Savanna brain just conveniently translates all of that complex quantum field interaction into a single sensation: solidity.
Exactly. It's just easier for your brain to say, ouch, solid object, than to process interacting quantum fields.
So let me get this straight. When I clap my hands together right now, nothing is actually touching in the classical sense. There is zero physical contact.
None whatsoever. What you're experiencing is just the resistance of invisible fields. The world feels so dense and absolute to us, but beneath that appearance, it's just a vast theater of forces operating in an unimaginable emptiness.
That is just wild to think about. But it seems to me the real problem here isn't just that the universe is overwhelmingly empty. I mean, we can sort of wrap our heads around empty space.
Sure.
The real cognitive barrier is that the stuff inside that emptiness, those fundamental particles, they refuse to behave like matter at all.
Right, they really do.
We expect them to be tiny, predictable specks. But the source text dives deep into the fact that if these solid particles aren't touching, how do they behave? We're dealing with something entirely uncategorizable.
Yeah, we are officially entering the territory of wave-particle duality here. And again, the text emphasizes how this just breaks our biological demand for neat, tidy categories.
We want things in boxes.
We really do. But light and matter itself, they behave in ways that systematically destroy those boundaries. Under certain measurement conditions, an electron behaves like a localized particle. You know, a distinct individual point with defined coordinates.
Like a little speck of dust.
Right. But under other conditions, that exact same electron behaves like a wave, a spreading continuous disturbance that can actually interfere with itself. Like throwing a tiny pebble into a calm lake and watching the ripples suddenly act like solid rocks.
To visualize this, I always like the analogy of a spinning coin on a table. instead of trying to imagine something that is somehow both a rock and a wave of water at the same time, which just hurts my head.
It's a great analogy, yeah.
Right. Because while that coin is actively spinning, it isn't heads and it isn't tails. It exists in this blur, a state of probability that basically encompasses both outcomes simultaneously.
Yes, exactly.
It's only when you physically slam your hand down on the coin, forcing it to stop, that it snaps into a single definitive state.
That captures the essence of quantum superposition perfectly.
Right.
The spinning coin is the wave function, which is just the probability distribution of where the particle could be.
Okay, so the blur is the math.
Right. And slamming your hand down is the act of measurement. That forces the universe to pick a definitive outcome. And the profound discomfort this causes us is that neither classical description, the wave or the particle, alone captures the full reality of the system.
Because in our everyday macro world, you can't just point to a physical wave in the ocean and call it a single solid object.
No, you can't. It doesn't make sense. Nature is just not obligated to respect our categories.
Our brains so aggressively demand that the universe pick a lane, You have to be either team wave or team particle.
But the authors point to that discomfort as the very engine of scientific progress. Reality has to come first. Our ideas come second.
Science changes its explanations to fit reality. Reality never changes to fit our explanations.
Beautifully said. When empirical data reviews that matter behaves in a way that just shatters our common sense, the scientific method dictates that we don't force the data into our limited mental boxes. We have to discard the box entirely.
But, precisely because matter behaves in these probabilistic shape-shifting ways, it leaves the door so wide open for profound misinterpretation.
Oh, absolutely.
I mean, if you look around online today, it is incredibly common to see quantum physics conflated with magic or mysticism. People take wave-particle duality and stretch it into these pseudoscientific claims about, manifestation or manipulating reality with just your thoughts.
And the text spends a significant amount of time dismantling that specific brand of quantum mysticism. It is crucial to draw a hard line here between a scientific theory that describes non-intuitive physical phenomena and just outright magic.
Right. It feels magical to us, but it's not.
Exactly. Quantum mechanics feels magical to a layperson because it defies classical mechanics. But it is, in fact, one of the most rigorously formulated, mathematically precise, and exhaustively tested frameworks in the history of human civilization. It is driven by extraordinary evidence, not mere speculation.
So what does this all mean for the history of it? Because I find it incredibly reassuring that the brilliant physicists who uncovered these rules in the 1920s didn't just accept them with open arms, they actually hated it.
They despised it. Einstein famously rejected the inherent randomness of it. He kept saying, God does not play dice.
Right. And he called quantum entanglement spooky action at a distance as an insult, trying to prove the theory had to be incomplete.
That historical reluctance is the hallmark of true empirical rigor. Scientists didn't invent a weird universe because they wanted to be esoteric or mystical. They were dragged into it, basically kicking and screaming by the data.
The evidence must always come before belief.
Yes. The math made predictions, experiments were conducted to test those predictions, and the results consistently favored the bizarre quantum model over the comfortable classical one. Evidence forced their hand. If we connect this to the bigger picture, the greatest strength of a scientist is not pretending to know everything. It's relentlessly asking questions and demanding evidence.
And the text also grounds us by acknowledging the current limits of this framework too, right? Because for all its predictive power, quantum mechanics actually has a massive glaring blind spot.
It does.
Yeah.
It fundamentally cannot be reconciled with gravity.
Right.
General relativity brilliantly maps the macro universe, the warping of space-time by massive objects like stars and black holes. And quantum mechanics flawlessly maps the micro-universe of atoms and forces.
But they don't play nice together.
Not at all. When you try to combine the two, like when you look at a black hole where immense gravity is compressed into a microscopic space, the mathematics just break down, they yield infinities, they stop making sense entirely.
Which is wild. We have two perfectly tested manuals for how the universe works, and they are written in completely incompatible languages.
It's one of the biggest mysteries in science today.
It just goes to show that science isn't about declaring we figured it out. It's about tolerating unresolved questions. And that logically brings us to the centerpiece of the source text, which is arguably the most debated, misunderstood concept in modern science, The observer effect.
Oh, yes, the observer effect.
We really have to unpack this carefully because the pop culture interpretation of the observer effect is the bedrock of all the mysticism we just discussed. The famous rumor is that simply observing something in quantum physics changes it.
That's the rumor, yes.
Like human consciousness has a physical effect on reality. If I watch a particle, it does one thing. If I look away, it does another. That's what people think it means.
And the source text just takes a scalpel to this misconception. This raises an important question about language, really. The confusion entirely stems from the scientific definition of the word observation versus our everyday colloquial definition.
Okay, how are they different?
Well, when an everyday person hears the word observe, they think of a passive act. You sit on a bench, you watch a bird fly by, and that bird is completely unaffected by your gaze.
Right, our eyes are just passively receiving ambient light that bounced off the bird. We aren't doing anything to it physically.
Exactly. But in the quantum realm, passive observation simply does not exist.
Period.
Period. To observe or measure a subatomic particle, you must interact with it physically. If you want to know the exact position of an electron, you can't just passively look at it. You have to bounce a photon of light off of it and measure how that photon returns to a detector.
And because an electron is so incredibly small, hitting it with a photon is basically like trying to figure out the location of a billiard ball by aggressively throwing another billiard ball at it in the dark.
That's a perfect way to put it. The very act of gathering the information transfers momentum. You disrupt the system to measure the system.
So observation in quantum mechanics is just a physical interaction.
Yes, it is an entanglement between the measuring device and the quantum system. It has absolutely nothing to do with human consciousness or mystical intention. A mindless automated sensor taking a measurement collapses a wave function just as effectively as a human being looking at a screen.
To really drive the mechanics of this home, the text dives into the legendary double-slit experiment. And they mention Richard Feynman here, who won the Nobel Prize. He famously stated that this single specific experiment contains the very heart of quantum mechanics.
You did. It is the purest demonstration of everything we've talked about today.
Let's actually walk through how this works step by step, because understanding the sequence of events is really what breaks your brain.
Let's do it. So the setup is deceptively simple. You have a barrier with 2 vertical slits in it and a screen behind that barrier to record what hits it.
Okay, got it.
Now, if you fire physical particles, let's say tiny paintballs, through those 2 slits, you get exactly what you expect. 2 vertical bands of paint on the back screen.
Classical mechanics, just marbles passing through holes.
Exactly. Now reset the experiment. If you send a wave of water through those 2 slits, the wave splits in half as it goes through. Those 2 new waves ripple outward and they intersect with each other on the other side.
Right, they overlap.
Yeah. Where the peaks of the waves meet, they amplify. Where a peak meets a trough, they cancel each other out. This creates what we call an interference pattern on the back screen, a series of multiple alternating bands of high and low intensity.
Okay, so far so good. Particles make 2 bands. Waves make a complex interference pattern of multiple bands.
Right. But then the physicists decided to fire quantum particles, like electrons or individual photons of light, at the slits.
And what happened?
When they fired a beam of electrons through the slits, the back screen showed an interference pattern, multiple bands.
Wait, really? So this proved that electrons, which we always thought of as solid little points of matter, were actually moving through space as waves, interfering with each other.
Exactly. But here is where the bottom just falls out of reality. The scientists thought, okay, maybe the electrons are just bumping into each other in midair. So they modified the experiment. They fired the electrons one by one.
Just one at a time.
Right. A single electron is fired. It goes through the barrier, hits the screen. They wait. They fire another one single electron at a time. There is absolutely nothing else in the air for it to interact with.
What pattern did they get?
Over time, as thousands of individual electrons hit the screen one by one, the pattern that emerged was not 2 discrete bands. It was, once again, a complex interference pattern.
That is just mind-blowing, meaning that a single solitary electron leaves the gun as a localized particle, somehow becomes a wave of probability as it travels, passes through both slits simultaneously, interferes with itself on the other side, and then suddenly snaps back into a localized particle the instant it hits the back screen.
It is the ultimate demonstration of superposition. The electron takes all possible paths simultaneously until a final physical interaction forces a definitive outcome.
But the physicists couldn't handle that, right? They desperately wanted to know which slit the electron was actually going through.
Of course they did. So they set up a detector, a measuring device, right at the slits to catch the electron in the act.
Okay, so they fire a single electron, the detector registers, it went through the left slit, and then the electron hits the back screen.
Yes, but the moment they did that, the moment they extracted that witch path information by interacting with the electron at the slits, the wave function collapsed.
Wait, what does that mean for the pattern?
The interference pattern completely vanished. The back screen simply showed two distinct bands, just like classical marbles.
Oh, wow. So just by demanding the information, just by forcing a physical interaction at the slits, the universe changed the behavior of the particle from a wave back to a classical particle.
Exactly. The rules of reality shifted, based entirely on the extraction of information. It proves that our classical concepts of trajectory and location are just utterly insufficient.
The universe really just exists in a state of interconnected probabilities until physical interactions force it into discrete realities. It is a lot to process, honestly.
It's completely paradigm shifting.
Well, let's pull all these threads together for everyone listening. We started today by acknowledging our biological limits. We're piloting biological hardware optimized for tracking lions on a macro scale savanna, meaning our baseline intuition is virtually useless for understanding the true foundation of reality.
Right. And then we examined how the solid world you feel around you is really an emergent illusion. It's born from the furious electromagnetic repulsion of particles that are themselves mostly empty space.
And we tackled wave-particle duality, proving that nature refuses to be neatly categorized by human logic. We distinguish between the rigorous empirical science that maps this weirdness and the pop culture mysticism that completely misunderstands it.
And finally, through the double-slit experiment, we saw how the very act of physical measurement forces a system of probabilities to collapse into a defined reality.
Relying solely on your everyday intuition really does leave you functionally blind to the true, magnificent mechanics of the universe.
It does. The scientific method and mathematics are genuinely the only reliable flashlights we have to navigate a universe that is far stranger than we are biologically permitted to imagine.
Which leaves us with a final, completely provocative thought to mull over until next time.
Oh, this is a good one.
We didn't explicitly dive into the biology of consciousness today, but consider this. The physical structure inside your skull, the neurons firing right now, generating your thoughts, your choices, your entire subjective experience of reality, that brain is made of atoms.
It's all matter.
Right. And the electrons and forces governing those atoms operate under the exact same bizarre, unpredictable quantum rules we just discussed. So if the deepest foundation of your biological hardware is a quantum system built on superposition and uncertainty, how much of your own consciousness and your own free will is fundamentally entangled with quantum mechanics?
It's a haunting question. Are the choices you make as deterministic as classical physics implies? Or is the spark of consciousness related to a wave function collapsing in the dark?
Think about that the next time you look at your hands. If the physical world is not what it seems, how much of what you believe about reality is based on rigorous evidence and how much is just the evolutionary limits of your own intuition? We'll see you on the next deep dive.